Oh, there's our fun noise. All right. So real quick, I'm just going to back it up. For those watching the video, I forgot to hit record when I started, but 1 is an opinion question. You can answer that how you would choose and explain why that's your choice. For number 2, earning 100% interest at the end of the year from this magical bank. If you put in 1,000 at the end of the year, you would end up with 2,000. Earning 100% interest means you're doubling your initial amount. All right, so now we're looking at number 3 here. So instead of being paid the 100% interest in one lump sum, it says, let's consider what happens when you get paid out multiple times a year in smaller increments. Okay, we're going to start by talking about interest that's earned quarterly. So how many times a year would that be if it's quarterly? Okay, so that's 4 times a year, every 3 months, right? So what will the amount of interest earned be? Will it be the same each quarter? What do you think? No, because if I put in $1,000 and then I'm earning a quarter of the interest, that's 25%, right? I'm earning 25% of the $1,000. And then the next quarter, I'd be earning 25% of that new amount, right? So this one is a no. And it's because the interest earned will be on increasing amounts. So each quarter, you'll have a larger balance that you're earning interest on. Okay. So for part B, they ask us to fill in the table to see how the money in the account is changing. Okay, we want to look at the initial amount invested is $1,000. So what's the percent interest earned each quarter? That's what I was just saying is they said 100% interest, but we're dividing it over quarters, 4 quarters. So we're doing 25% per quarter. Everybody okay with that? All right. Now, after the first quarter then, how much money am I going to have in the account? How do I calculate that? Right. So 25% of 1,000 is the interest plus the original 1,000. So thinking about what we talked about last week with exponentials, that's saying your initial amount, 1,000, times 1 plus the rate, right? So wouldn't that be 1.25? So if I just multiply that, that's how much should be in the account after the first quarter. Okay, so that is $1,250. Okay, now what do I do to figure out how much is going to be in the account after the second quarter? So I changed the initial amount now to $1,250 because that's now the balance in the account that I'm multiplying by 1.25. Okay, so that's going to go up to $1,562.50. Then don't I do the same thing? I'll bring that amount up and multiply by 1.25 to see how much I have at the end of the third quarter. And that comes out to 1953.13. Then at the end of the year, so that's at the last quarter, the fourth quarter, I'll take the 1953.13 and multiply by the 1.25. And so I'll end up with $2,441.41. Everybody good with how I calculated that? Now that can get kind of tedious, can't it? If I kept having to do that. Okay, so that's why we have formulas that will calculate that for us so that we don't have to recalculate after each time it's being compounded. Okay, in this case, quarterly. Okay, so how does the amount in the account after 1 year compare to the answer from question 2? If they just straight up gave us 100%, we said we'd have $2,000. So doing it this way, it was higher, right? We got a better return. Okay, so it's bigger, more, if the interest earned every quarter. And the reason is because interest earns interest. So you're making money on money you didn't initially have. Interest earns interest. Okay. So the next question says, is it even better to earn your interest monthly or weekly? What about daily? And we're going to fill in the next table. But before we do that, what's your prediction? Do you think you're going to what do you think is going to earn you the most money? You'll end up with the most money at the end of it, getting it quarterly, monthly, weekly, daily? Daily? Okay. So let's verify. Let's say, okay, so the number of payouts each year. So when they say monthly, quarterly was 4 times a year. What's monthly? Okay, weekly. I'm going to do the different lines in different colors here. And daily. Now, actually, we're going to be as accurate as we can, taking into account leap year that happens an extra day every 4 years. We're going to put 0.25. Because if this continues past 1 year, if you were to keep this going, you would eventually get to a leap year with an extra day, right? Okay, so that's why we're going to do that. All right, so let's start with the monthly. So the percent interest earned each pay period. So we're taking that 100% interest and we're dividing it over 12 payouts. So that is going to be what percent? Y'all can have out your calculators if you have one, or you can use your phone for a calculator if you want. Say it again. 8.3%. Okay, so this will be every month they'll calculate an 8.3% addition to the account. 8.3% on the balance. Okay, so amount in the account at the end of the year. So my initial amount is $1,000. Okay, if we're doing 8.3%, what is my base of my exponential going to be here? Good. Remember, it was 1 plus the rate as a decimal. Okay, now, instead of going through this 12 times like we did in the previous question, going through it 4 times for quarterly, what math could we do instead? Yeah, because each one of these, we just kept multiplying the previous answer by 1.25, didn't we? So couldn't we have just put an exponent on the 1.25 and kept the initial amount, the 1,000? Okay, so that's the exponential equation we learned last year, last week. You did also learn it last year, though, in Algebra 2. But the a times b to the power of x. Okay, so A is the initial amount, which we're saying is $1,000. B, that's the base. And then the exponent is going to be at the end of the year. How many times will we have done this? 12. Okay, so we can calculate this once to get the balance at the end of the year rather than having to go through that process like we did on the previous example. So I'm going to go ahead and tell you what this comes out to save us some time. This comes out to $2,603.40. Okay, so we're going to do the same thing for weekly. So we would take the 100% and divide by 52. And that's going to put our rate at 1.92%. Okay, so my initial amount has not changed. It's still 1,000, but what's going to be my base now? Since that percent changed. Yeah, 1.0192. I'll go ahead and put all those places. Okay, and what's the power going to be this time? To the 52nd power. Very good. So that one is going to come out to $2,688.37. So it looks like y'all's prediction is correct. The more often we're compounding it, the higher the amount is in the account at the end of the year. Okay, so I think the daily will be the highest, but we'll confirm. So if we do 100 divided by 365.25, that's going to put our percent at 0.274%. So I'll have $1,000. Now this one's going to be 1.00274. And this will be to the 365.25 power. .25 power. Okay, so this one comes out to be a little bit more. It's $2,716.70. So number 6 says, do you think you can triple your money if you received payments multiple times a day? So if they're giving you 100% interest, do you think you'll ever triple your value, triple your money? No. I mean, it's getting pretty high. It's like the more often we compound it, but like if we did it twice a day or 3 times a day, what's happening to this percent each time you increase the number of times that it's compounded? That percent is decreasing. So yes, the amount that's in the account is increasing, but notice it's increasing by less and less. So it's increasing more slowly as it's compounded more often. So eventually that's going to trickle out. What does that mean graphically? What is that going to look like? It's going to look like an asymptote. It's the end behavior of that graph is going to approach some certain number, but it won't actually ever triple. Does that make sense? Okay, so kind of, I mean, you can write that in your own words however you'd want, but I would say no, or probably not. The amount is increasing more slowly as it's compounded more often. So it gets to be a smaller and smaller percent each time you compound it. So that's going to grow at smaller and smaller increments. Okay, what's the most money you could have in your account after 1 year with the same initial investment of $1,000? So it's, if you did this, we said daily was $27.16. So I guess if they did it multiple times a day, it would get higher than that, but not significantly, right? So maybe something between 27 and 2,800. Like it'll get higher than this, but not too much higher. I mean, we're just estimating right now. So maybe about 27 to 2,800, somewhere in that range. Y'all okay with that estimate? Okay. Now, to figure this out, let's come up with an equation for what we did in this table for future use. So we took the initial amount, okay, so our starting amount, and what we multiplied it by was 1 plus, and then where did we get this 0.083 or 0.0192 or 0.00247? That came from doing the rate, the 100%, right? Divided by how many times it's compounded. Do y'all agree? Okay. So the number of times it's compounded, and then we raised it to the power. What power did we raise it to? The same as what we divided this by, right? So that n. When you're doing this, if you were to continuously compound it, that n would be approaching infinity, wouldn't it? So as this graph approaches infinity, it's the right-hand end behavior. What is our function approaching? That's what we would be looking for to figure out what's the most money you could make. Good? All right, let's flip it over. Take some notes here on this compound interest formula. Not that one. That 1, 2, 3. Not that one. Huh, maybe I didn't get it. Let me get a snip of this other page real fast. I thought I copied it over already. Not gonna let me do it. I gotta get it over here. Yes. Okay. All right. So the compound interest formula and the continuous compounding interest formula, you may recognize from last year in Algebra 2, but we're just off to the side here. We're going to jot down what all of those different values or what all those different variables represent. Okay, so I'm going to try and kind of color code this. So we'll start with P sub 0. That is your initial amount. Okay, if we're talking in finance, that's like your investment, your initial investment. You'll often hear the word principal. That's the principal amount. That's what you started with. Okay, then let's look at the R. Okay, that's the interest rate. Now, in the examples on the previous page when we were looking at this, we were using 100% interest from a magical bank. That's not real. Nobody's going to give you 100% interest. So it's whatever interest rate is being offered or charged. This could be like on debt and you're paying the interest instead of earning the interest. Okay, and it needs to be written as a decimal, converted from a percent. Okay, and then N we said is the what? What did we divide by? The number of times it's compounded per year. Okay, now you'll notice in this exponent here for this one, it's not just in, it's in T. Okay, on the previous page, we weren't multiplying by T because everything we were calculating was at the end of 1 year. So multiplying by 1 wasn't going to change anything. Okay, but T is actually up there, and T is the number of years. So you could calculate the interest earned past the end of the first year. You could say in 30 years when I retire, what's my account going to be at for my 401k or whatever my investment is. Okay, so you can calculate it for years down the road using the number of times compounded per year, the interest rate, and the initial amount. Okay, now the P of T, what you're finding, that is the annuitized amount, the amount after the interest has been earned or the interest has been charged. Okay. In continuous compounding, you'll notice the difference is we still have our initial investment P and we still have an exponential, but the base that's being raised to the power is now what's called an E. Okay. That E is its own number, kind of like pi is its own number. E is its own number. It's not a variable. Okay. E is the base rate for all continuous growth. So maybe you remember last year, and maybe even in some of your science classes, where y'all maybe did growth and decay of like particles or substances, right? Like the decay rate or the growth rate of something. Did y'all do that? So y'all used the continuous compound formula. So it's not just for finance, it's for any continuous growth. It doesn't have to be money, okay? But if something is continuously growing, you're going to use this base E, okay? Now, E is approximately 2.718. If you forget that, there is a button on your calculator for E, just like there is for pi. Show you. So hopefully you remember this, but if not, figure that out. Okay, so E is right here in blue. It says e to the x, okay, above the natural log button, the ln. So to get e, you could use that button. I'm trying to think. I think there's another place above what? Oh, well, that is, oh yeah, no, that is E. That's not the alphabet's in green, so it's not the green E. But this lowercase e in blue above divide. So you could use either one of those locations. So if I hit second divide, that gives me E, and you can see that's the value. Okay, or if I end up needing to raise e to a power, I can do second natural log, and it goes ahead and has the place for the power for me. Okay, so e to the 1 power, that would give me the same value. Okay, so when we're doing continuous growth or decay, we use e. And then the r is in the power, it's RT, the rate times the number of years. So this is, you'll sometimes hear people say PERT, use the PERT formula because it's PERT, P times E to the power of RT. So far, so good? Okay, now let's look at that next example. Estimates of the number in millions of US households with digital televisions is given by, it says D equals 30.92 times 1.012 to the power of T, where T represents the years after 2000. So the initial time when this begins is 2000. That would be when T is 0, is year 2000. Okay, so this is your general exponential model. Okay, if you have forgotten, I'll write it off to the side. Okay, remember it's y equals a times b to the power of x. Okay, so we need to remember that the initial amount is the a. In this case, the 30.92. And this question asks us what that represents down here in the context of this problem. We'll answer that in a second. And then your B, that's your base rate, your percent change, is the 1.012. And what does that represent in the context of this problem? We'll answer in just a second. All right, so let's get back to it. So part A says, is the number of households with digital televisions increasing or decreasing? Yeah, and how do you know that? Yeah, that number is greater than 1. So it's increasing. If it was decreasing, we would have done 1 minus the rate. And so you would have ended up with a number between 0 and 1 for your B. Okay, so since B is greater than 1, this is an increasing. It's growth. All right, now what do those numbers represent in the context of this problem? See, I'll color code this for you. So the initial amount, I just kind of told you when I was talking about T and the year 2000, this would represent what? The initial amount of what? What is this? What's the context of this problem? Yeah, this is in millions. So there's 30.92 million households that have a digital TV already in the year 2000. That's what that means. Okay. 30.92 million households I'm just going to abbreviate DTV for digital TV. So digital TV in the year 2000. Okay, this is when T equals 0, if you want to think of it that way. All right, and then in what I highlighted in green, that represents what? It's the percent change of the households with digital TV, right? Okay, so this is, hey, all right, yeah, go ahead. So the percent change of households, no problem, with the digital TV. So are we good with understanding what the parts of the equation represent in the context? Yeah, because a lot of times exponential growth and stuff, it's going to be in real world situations. It's going to be word problems. You have to understand, what do these numbers actually represent? Okay. All right. Then C says, now use the model to estimate the number of households with a digital TV in 2015. How would I do that? In 2015 tells me what to plug in where. 15 for T. Because this is starting, this T is the years after 2000. So 2015 is 15 years later. So we're plugging in 15 for T. Okay, so that is going to come out to approximately 36.978. And again, this is in million households. Have digital TV in 2015. We feel okay about that one? Good. Okay. Y'all kind of remembering this? Is this coming back to you from Algebra 2? Kind of, sort of. All right. So in the next example, it says on the day of a child's birth, a deposit of $25,000 is made into a trust fund that pays 8.75% interest. Determine the balance of this account on the child's 25th birthday if interest is compounded weekly, monthly, and continuously. Man, I wish I was that baby. That would have been nice. All right, so I've gone ahead and pre-written out the formula, okay? So they told us 25,000 is the initial amount, okay? And then we said our compound interest formula is 1 plus, and then the rate as a decimal, so 0.0875 over n, the number of times it's compounded per year, and then that's to the power of nt. And our time is 25 because it says on their 25th birthday. So that becomes 25n as our power. Everybody okay with how I set up the equation? Okay, so now I'm going to plug in. I'm going to do this three times. First, I'm going to plug in weekly. So what am I plugging in for n? 52, because weekly would be compounded 52 times. Now, I'm not going to show the calculations in the calculator for every single one of these. I'm going to save us some time and just tell you what they come out to. But I highly recommend you plug this in at some point. If not now, try it tonight. Plug this into your calculator and make sure you get the same number I'm giving you. Otherwise, you may have an issue with how you're typing it in, and we need to make sure we clarify any questions about that. Okay, so this is what I'm calculating for weekly, and it comes out to $222,413.32. At the age of 25, man, can't imagine. All right, so then monthly, what would I be plugging in? So if we're compounding monthly, I'm going to change both of the, where I had 52 plugged in, I'm going to change both of those to 12. Okay. And I'll tell you, you think it's going to be more or less than weekly? Yeah, monthly is calculated less often, so you're not going to have earned as much interest. So that would be $221,061.10. Okay, we'll go ahead and calculate the rest of these. Let's see, is it all about turing? Oh no, we can finish this one continuously, but then we'll do that last example tomorrow. I'm going to go ahead and finish continuously. Continuously is a whole separate formula, right? Continuously is the same initial amount, but then it's times E to the RT. So R is 0.0875, and then the T, the time, is still 25 years later. That's what we're trying to figure out. So that one, when I calculate, comes out to 222,822.57. That one was for continuously. Y'all feel okay about that? All right. So again, no new assignment today. Just finish keep working on the Delta math from yesterday if you did not finish yet. And then tomorrow we'll finish up this last example this is 7.5, and we'll start talking about 7.6. We are going to have a new practice assignment tomorrow after we talk about 7.6. So I'd really try and finish up that Delta math tonight, so then you don't have two assignments at the same time. Y'all have a good one.